Hello everyone, welcome to lecture 14 of the online course on modern display technologies, flat panel displays. Today's lecture will be on elastic deformation of liquid crystals, and we will cover some of the properties of electromagnetic waves, which will be important to understand this deformation properties of liquid crystals. So here's the lecture outline. We will consider the liquid crystal director elastic deformation. We will talk about the reasons behind elastic deformation and desalination. Also, we will discuss the escape of liquid crystal director in desalinations. Then we will move on to the electromagnetic waves, discuss briefly about the Maxwell's equation and boundary conditions. We have seen those, but we will revise those because it will be useful in the context of liquid crystals. We will discuss about the curl equations and wave equations. Then we will discuss about the wave propagation and the transverse nature. This very briefly we will do. And finally, we will talk about the field relations and the energy in electromagnetic waves. So let us first look into this liquid crystal directors elastic deformation. Now, what is this elastic deformation that liquid crystal director faces? These are basically the spatial distortion of the average molecular orientation, which is also called the director in the case of the liquid crystal. Now, this deformation is caused mainly due to external influences such as electric fields, magnetic fields, surfaces, temperature gradients, or mechanical stress. This director is usually represented as NR, where N is basically the unit vector that indicates the average alignment direction of the liquid crystal molecules. So we have seen this before, but I am just giving you a quick recap because that will be useful in this lecture. So when you consider the nematic liquid crystals, the distortion of the director basically costs some elastic energy, and this is described by the Frank-Ocean elastic theory. So what is that? The total elastic free energy density can be written as F equals half K11 del dot n whole square plus half K22 n dot curl of n whole square plus half K33 n cross curl of n whole square. Now you see that these are the three coefficients here. So the first one, K11, is called the splay elastic constant. K22 corresponds to the twist kind of deformation, and K33 corresponds to a bending kind of deformation. So these three are basically the three fundamental deformation modes of liquid crystal that you have seen. Now, why director deformation costs energy? Now, you need to understand that in the ground state, the nematic liquid crystal director is spatially uniform. So when n, this director is getting, so here I am using both the notations, either you can use them using n in boldface, or you can use n with this arrow symbol on the top. That's the vector, that's the director, right? So when n is deformed, there is always elastic energy. So deformations will cost elastic energy, but why it occurs? It basically occurs due to the surface anchoring, confinement, impurities, irregularities, or external field which is being applied on the liquid crystals. So you can understand the different deformation that you have seen may be associated with different kind of costs, and the deformations can transform into one another to minimize the energy. So if you talk about the elastic deformation and declination, let us first consider a possible deformation of the pneumatic liquid crystal, which is confined between two parallel substrates. So you can visualize this. Okay. So you will have tangential anchoring condition here, where the molecules basically align parallel to the substrate, and in the in-plane direction on the substrate surface, there is no preferred direction or orientation. So if you assume a one elastic constant approximation, in that case all these different coefficients k11, k22 and k33, they can be considered to be equal to k. That means the splay, the twist and the bend, okay, they all have the equal constants. So in such an approximation, the elastic free energy density, which was expressed earlier like this F, now all these can be replaced. This k11, k22 and k33 can all be replaced with k. So once again, the first term tells you about the splay deformation, the second term tells you about the twist deformation, and the third term tells you about the bend deformation. So now, having this, you can use a vector decomposition identity, something like this, where curl of n modulus whole square can be written as n dot curl of n whole square plus n cross curl of n modulus whole square. Okay. So this can be basically taken here, and you can write these two terms as this. So this elastic free energy density can be written in a simplified form as half k del dot n, that is the divergence of n whole square, plus half k curl of n whole square. So this is a simplified version of the elastic free energy density under one elastic constant approximation. So what is the main idea here? So here you can see that the total energy basically includes the contributions from splay, twist and bend altogether. So in this case, the planar director field lies between the tangential substrates, as we mentioned. So this is resulting into tangential anchoring. So the director is basically lying on the substrate's xy plane. So you can basically represent the director. Director is a vector, right, and you are in the xy plane. So you can basically express it as cos theta xy x cap, and then you can write plus sin theta xy y cap. So theta is basically the angle between the director and the x-axis. Okay. So when you substitute this form of n vector into the free elastic energy density equation F, this will basically result into this simplified expression, which is F equals half k dou theta by dou x whole square plus dou theta by dou y whole square. Now if you want to minimize the energy using the Euler-Lagrange method, which basically gives the Laplace equation, where dou square theta by dou x square plus dou square theta by dou y square will be equal to 0. Okay. Now when you switch from Cartesian coordinates to cylindrical coordinate, this above equation can be written in this particular form, that is 1 over r dou r times r dou theta dou r plus 1 over r square dou square theta dou phi square equals 0. So this was in the Cartesian coordinates, this is in the cylindrical coordinates. Now with this you can understand the declination and the singularities. Okay. So in cylindrical coordinates, you will see if theta depends only on the azimuthal angle phi, then you can write theta equals S phi plus theta naught, where S basically tells you about the strength of the desalination. So, this desalinations are basically kind of line defects that you see in liquid crystals, where the orientation of the molecules, or you can say the director, changes abruptly. So, that basically creates singular points or lines within the material. Okay. So, they basically occur primarily in the nematic crystals, okay, and they present topological singularities where the molecular alignment are not defined. So, you can also understand that the director n cap and or the n bar and minus n bar, they are basically equivalent, right. In that case, 2 pi s can be written as plus minus m pi, okay. So, s can be written as plus minus m by 2, where m is basically 0, 1, 2 and other integers. So, this basically tells you about the allowed desalination strength, which can be 0, plus minus half, plus minus 1, plus minus 3 by 2 and so on. Okay. So, with that you can understand the different configurations of the liquid crystal director in the case of desalinations of various strength. So, figure 5 basically shows this. Here the liquid crystal director configurations for deformations with different variety of S, which is the desalination strength, and theta naught values are shown. So, this one is for S equals half, theta naught equals 0, okay, and this is for S equals minus half, theta naught equals pi. This is for S equals 1, theta naught equals pi. This is S equals minus 1, theta naught equals pi. This is for S equals plus 1, theta naught is pi by 2. Here it is minus 1, theta naught is pi by 2. So, what you observe here is that at the center you can see there is a singularity or discontinuity. So, in the liquid crystal cell, this creates a configuration with a central line singularity, which is known as the desalination. Now, if you carefully observe these patterns, you will see that the positive value of S means that the director is basically rotating in the counterclockwise direction. Okay, when you have like this, when you have S equals negative, okay, in this case the director basically rotates clockwise. You can also calculate the energy, elastic energy density of the desalination using this formula, F equals K S square divided by 2 R square. So, what you see that the elastic energy is basically proportional to the square of the strength of the desalination, and the energy will diverge when this radius becomes 0. That means it is becoming a very sharp turn, or there is a singularity. So, whenever there is a singularity, the energy basically diverges. So, now let us focus into escape of this liquid crystal director in desalination. So, to avoid this infinite energy at the core, the liquid crystal can undergo an escape. So, what is that escape? There are basically 3 escape routes for cylindrical desalination. So, this is the first one. It shows that it basically transforms into isotropic phase at the center with a radius of RC. So, these are 3 basically orientation, okay, or you can say 3 escape routes. So, here you are basically having escape from splay to isotropic at the core. Here you have escape from splay to band. Here you have escape from band to twist. Okay. So, this is the first one where you can see that you are basically transforming into a isotropic phase at the corner, okay, so at the center. So the center radius is considered to be RC. So it basically keep the radial splay that you see here far from the center, but it's essentially replacing the center with some sort of isotropic material. In the second escape route, okay, this basically escape into the third dimension to band the deformation. So that you can see here. So from splay you are going into the banding. So here what is happening? You are basically tilting the director towards the cylinder radius so that your singular core basically disappears. So you are not getting that singularity anymore. The third route is basically it's an escape from band to twist. So how you are doing here? You are doing the further reduction of the energy by introducing twist. So your director here is basically twists out of this RZ plane to further reduce the band energy when your K22 is significantly small. So the director twists out of this RZ plane to further reduce the band energy when K22 is sufficiently small. So what we understand here is that defect cores cannot remain singular. The system must find a low energy escape route to solve it. So that is the concept behind this escape of the liquid crystal detector in desalination. So with this, let us now move on to the fundamentals of the electromagnetic wave, and I want to go a little faster in this case because all of you must be knowing about these concepts. So this is just a brush up and a build up for the next lectures where you will be using these concepts for the liquid crystals to understand them better. So in wave theory, we have seen that light is basically electromagnetic wave propagating in space. So there are four fundamental vector quantities. One is the electric field given as capital E, the unit is volt per meter. Then you have electric displacement represented as capital D, its unit is coulomb per meter square. Then you have magnetic field H, capital H, ampere per meter is the unit, and then you have magnetic induction or magnetic displacement, okay. So that is represented as B, okay. So that is basically having the unit of Tesla, which is volt second per meter square. So what is the constitutive relation? So this is where the electromagnetic waves are now interacting with the matter. So this is your light, and this is where the light or the electromagnetic wave starts interacting with matter, and that is defined by the constitutive relations. So D can be written as epsilon naught epsilon E. So epsilon naught is basically 8.85 into 10 to the minus 12 farad per meter, and epsilon, you see this is basically a tensor. So this is the relative dielectric tensor of that medium. So what is the value of epsilon naught? It's 8.85 into 10 to the minus 12 farad per meter. Similarly, for magnetic fields, you have this magnetic induction or magnetic displacement given as mu naught into you have the mu tensor, which is the relative permeability tensor of the material, and then you have H, that is the magnetic field. So this is how electric field and its displacement are related. This is how magnetic field and the displacement is related. So here mu naught is a constant, which is the vacuum permeability, right, and it is given as 4 pi into 10 to the minus 7 Henry per meter, okay. So the electric displacement relates to E, as I mentioned, via this permeability tensor. On the other hand, magnetic induction relates to the magnetic field via permeability tensor. This is the permittivity tensor, right. So now let us focus this concept on liquid crystals. There we need to keep in mind that the liquid crystals are basically non-magnetic media. So that sets our permeability to be close to 1. Okay, so you can basically put this permeability tensor to a identity tensor. Okay, so this simplifies the analysis significantly. Now let's talk about the Maxwell's equation. So Maxwell's equation is the one that can tell you how the electric and the magnetic fields are interacting with each other, okay, for a electromagnetic wave that can be in a vacuum or in a medium. So let us first start with the Maxwell's equation, where in a medium where no source is present. So if you consider a medium without any free charge, the electromagnetic wave can be governed by the divergence equation that tells you the divergence of D equals 0. So which basically tells that there are no electric charges present. Then you have divergence of B equals 0. That means the magnetic field lines are not divergent. That means no magnetic monopole basically exists. Then you have two curl equations. The first one is the curl of E vector, that is given as minus dou B dot T. So this is basically known as the Faraday's law. These are also known as the Gauss law of electric fields. This is the Gauss law for the magnetic fields, okay, or magnetostatics, you can say. This is the Faraday's law. So here you can see that changing B or magnetic induction basically induces curl of E. Curl of E means rotation in the electric field vector. The second curl equation is curl of H, which is minus dou D dot T. This is known as Ampere's law. So here you can see that the changing electric displacement with time induces curl in the magnetic field. Now if you have a boundary between two different media, okay, you have to apply the boundary conditions. So let us consider there are two medium like this. One is having epsilon 1 mu 1 as the permittivity and permeability. The other one has got epsilon 2 and mu 2. Now this is the interface of the boundary between the two materials. So say a wave is kind of propagating like this. So what will happen to the wave at this particular interface? So we'll see that the normal components of the displacement fields like D and B and the tangential components of the electric and the magnetic fields, they are continuous across the boundary. So if you try to write this in terms of equation, so this is your medium 1, this is medium 2. So displacement fields are like D2n minus D1n equals 0 and B2n minus B1n equals 0. N stands for the normal components. Okay. However, the tangential components will be the one that is lying along the interface. So the tangential components of the electric field and the magnetic field are continuous. So E2t minus E1t equals 0 and H2t minus H1t equals 0, right? So that way you can write this. Here the representation is bit generic because here you are just using A, that basically represents any of these vector fields, and N is basically showing you the unit normal to the interface. Small n is the normal component and small t tells you about the tangential component. Now in the case of isotropic medium, where the properties are same in all direction, your constitutive relations become simpler. You do not need to use a tensor for permittivity as well as permeability. You can simply use that same value, okay. So the equations looks much simpler. So you can also put this into your Maxwell's equation, which is defined as divergence of D. Now instead of D you can write epsilon naught epsilon E, okay. So the whole thing can be written as epsilon naught epsilon del dot E equals 0. The same thing you can do for the magnetic equation also. So divergence of B, now B can be replaced by mu naught mu r H. This is relative permittivity. Somebody tells it mu r, someone keeps it simply mu, okay. So you can put it here, take these constants out, so you get delta H equals 0, okay. So now since in this case the epsilon and the mu are basically scalars, they are not tensors in the case of isotropic medium, they can be basically factored out of this divergence operator and you can see that the equations become much more simpler. What happens to the curl equations? So the curl equation in the case of isotropic uniform medium will look like this: curl of E equals minus dou B dot T. B can be now replaced as mu naught mu H. So the equation looks like this. Similarly, for the second curl equation, dot D dot T, D can be replaced by epsilon naught epsilon into E. Okay, makes sense? Now with this too, if you take curl of this equation, so you make curl of E will give you a curl on the right hand side also. So you can write minus mu naught mu dou dot T curl of H. Okay, and curl of E can be written as gradient of divergence of E minus del square E. Now in a source free medium, divergence of E will be 0, so this term becomes 0, so you just have minus del square E. What you have here is basically minus, because you are taking curl of this equation, so you have curl here also, you have minus mu naught mu dou dot T curl of H. Then curl of H you can put from here. So when you substitute that, the minus here and the minus here is removed, so you simply get del square E equals mu naught mu epsilon naught epsilon. So all these 4 terms will come here and you get dou square E dot E square. Okay, so this equation is called the wave equation. Okay, so this is the wave equation. So you need to look for a solution to this wave equation. So one proposed solution is that you can write for monochromatic wave, the complex function formalism can be of this particular form, where E of E, that is the electric field, which is a function of r and t, space and time, can be written as E naught or e to the power I omega t minus kr. So E naught is basically the amplitude, omega is the angular frequency, k here you see is basically the wave vector's magnitude, that is 2 pi by lambda. Lambda is here very important, which is the wavelength in that particular medium, not in the vacuum. Okay, so this is the solution to this particular wave equation. So with that we can also find out other properties like the dispersion relation. So if you substitute this equation into the wave equation, you can also see there is a relationship between the omega and the k. Okay, there is the angular frequency and the wave vector, that turns out to be omega square by k square equals 1 over epsilon naught mu naught epsilon mu. So this one is the dispersion relation. So omega k is also called the velocity v. Okay, so that is the propagation velocity, or you can say this is the phase velocity. So that comes out to be square root of this right hand side, that is square root of 1 over epsilon naught mu naught epsilon mu. In the case of vacuum, this epsilon and mu both are 1. Okay, so your v will be same as c, right, that is 3 into 10 to the power 8 meter per second. Now in case of non-magnetic medium, so you can relate v and c, because in the case of non-magnetic medium means mu is 1, okay, all other terms exist. So what you have, v equals c divided by square root of epsilon. Now square root of epsilon can be also written as n, which is the refractive index. So you will see that you get the equation v equals c by n. Here you should remember that epsilon can be also frequency dependent. Finally, you can also calculate what is the wave vector k, that is 2 pi by lambda. Okay, so you can write it also as 2 pi n by lambda naught. Okay, so if you want to see this in terms of how it has come, so you can basically get it from here, that k is basically omega by v. Okay, v you can write as c by n. Okay, so n goes up and you get this relationship. So lambda naught, remember this is the wavelength in vacuum, and n is the refractive index of the medium. Now when you have transverse wave, so you can see that from the equation del dot D equals 0. If you apply this to the electromagnetic wave equation, okay, you get that del dot D equals minus I d naught e to the power I omega t minus k dot r equals 0. So, what is the key conclusion in this case? D is basically perpendicular to the propagation direction k. So, this holds even in the case of anisotropic media. That means this established that the light is a transverse wave where the electric field direction is basically orthogonal to the propagation direction. So, E is also perpendicular to k in isotropic media, but not in the case of anisotropic media. So, this holds for D, but in anisotropic media the D and E relationship depends on epsilon, and if epsilon comes with a tensor in the case of anisotropic, so your E electric field may not be perpendicular to propagation direction in the case of anisotropic media, but this relation holds good for the displacement field D. So, the final comparison here in terms of field relations and energy in EM waves. So, you can do some operator substitution. So, in a homogeneous isotropic medium for monochromatic waves that you have seen earlier, so you can put dot dot t equals I omega, and this del can be put as minus I k. So, these two will basically simplify the differentiation and gradient into algebraic operation. So, we can see how it looks like. So, we are basically going into the frequency domain now, right, from time domain to the frequency domain. So, if you take this curl equation, curl of E is minus W dot T, which is basically minus mu naught mu dot H by dot T. So, if you put this as dot T as I omega, so you can replace this equation and you can have a simple form like this. Okay. So, I am not doing this, you can do this back of the envelope calculation, that your del operator is basically this and your dot dot T is minus I omega. So, you will get B equals k cross E divided by omega. So, what do you see here, that B and E are orthogonal to each other and their magnitudes are basically related. So, the magnitude of the magnetic induction of the magnetic displacement, you can say, is basically n by c times the magnitude of the electric field vector. So, this will be very useful in the case of Fresnel reflection and other cases. Okay. So, try to remember this. Next, we look into the energy density. So, the density of the EM wave can be given as U as half E dot D plus H dot B. You can also find out the energy flux, which is going in the direction of the Poynting vector, given by capital S, which is basically E cross H. And the magnitude of this Poynting vector can be calculated as n divided by mu naught c into E square. So, what are the important summary of this key relations? The first thing is that D, the electric displacement, is always perpendicular to the propagation direction. This is also true in the case of anisotropic medium. It is true in the case of isotropic, also it is true in the anisotropic medium. For E, it is only true in the case of isotropic medium. We have also seen that the B and E are basically orthogonal fields, and the Poynting vector S, which is the cross product of E and H vectors, that basically gives the energy flow direction. So, with that we will conclude our lecture here. If you have any query regarding this lecture, drop an email to this email address mentioning the course name and the lecture number in the subject line. Thank you.